Okay, this is lecture number 26 of EE 503, and we are continuing with the fourth type of random processes. This is called periodic processes. So as a reminder, we have previously studied moving average processes, autoregressive processes, and Armel processes. So this is the last type for Weisstein stationary processes, which we call periodic processes. Sometimes this is also called harmonic process. Well, let's start with a reminder. Let's remember that autocorrelation Kate lag is in magnitude less than or equal to autocorrelation zeroth lag. Since this is already a real number, and it's called for zero mean process, it's the variance, okay? So it's a positive quantity. I'm not putting even a magnitude over here, okay? So how can I, let's say prove that? Well, previously we have studied such things, in detail, but for example, here's one proof. Let's say that I have this autocorrelation matrix like this. So this is Rx0, Rx minus 1. So this is Rx of minus k, okay? So this goes maybe Rx of minus n, okay? So this is a symmetric matrix. I'm assuming that all of them are real quantities, and so on. Okay, so this goes like this, Rx0, Rx0. So this is an n plus 1 times n plus 1 autocorrelation matrix. This is Rx of n. Well, that is it. Now, the entries of interest, let's say that this is the zeroth entry, or zeroth column. So this is the kth column, and so on. So let me also mark, for example, kth row over here. Then on the kth row, I have Rx of k. Okay. Next, Rx of k minus 1. So on. Okay, something like that. So if I on this kk row, let's say, let me put it over here, I have Rx of 0, okay, on the diagonal. Very good. So this is my autocorrelation matrix. So how do I calculate this autocorrelation matrix? This is the expected value of x times, let's say, x transpose, where this x is equal to x of n, x of n plus 1, x of n plus n. So this is n plus 1 times one-dimensional vector. So x times x transposes n plus 1 by n plus 1, n plus 1 times n plus 1 matrix, and its expectation is this autocorrelation matrix. So I know that this matrix is positive semi-definite, okay? So how about this? If I multiply this matrix by, from left and right, by, let's say, this vector. So it's 1, 0, this is minus 1, so this is again index 0, this is index k, it's all zeros are there. Okay. So at the zeroth index of this vector I have 1, at the kth index I have minus 1, and let me have this vector transpose over here. Okay. So I have 1, 0, 0, then somewhere minus 1, and the rest is also 0. So what do I have? Well, due to the positive definiteness, I know that for any vector, this has to be greater than or equal to 0 by the positive definiteness. Okay? But if I do this multiplication, so this vector on the right selects you may say it multiplies second row, second column, third column, and all of those columns except the 0th and the kth column by 0. Okay? So if you do this operation, you see that this element is multiplied by 1 and 1. This element is multiplied by 1 and it's multiplied by -1 and so on. So if you do this operation, you see that this singles out these entries of this matrix. Okay, so at the end, this leads to the following: 2Rx0 minus 2, not 2, but Rx of k minus Rx of minus k greater than 0. But these are due to the symmetry, they are equal to each other. Then we see the following: Rx of k less than or equal to Rx of 0. Okay? So we get a result like that. Okay? Now, I can make this plus or minus 1. So I can change the sign of this. If you want, I can put plus, or I can put plus also over here. Okay? So then I can put plus also over here. Then I can put plus minus over here. Okay? Or this is moving to the other side, less than or equal to 0. That means that Rx of k, sign is not important, less than or equal to Rx of 0. Okay? Because it can be multiplied by plus or minus 1, I get the same result. Well, this is one proof by the definition of the positive definiteness of the autocorrelation matrix. So about another one. Well, how about this? Let me see. The expected value of z times w is less than or equal to expected value of z, expected value of z square, w square, square root. Do you remember this? This is what we call Cauchy-Schwarz inequality. Okay? Or, you know, this is the inner product is less than or equal to product of the norms. Okay? Well, we can interpret it like that. Now, how about this? Now, let me, instead of z, let me introduce x of n. Instead of w, let me introduce n minus k. Okay? For this one w. Then, over here, on the left side, I have Rx of k in magnitude. Less than or equal to, this is even easier, as you see, by, you know, Cauchy-Schwarz, you might say. Or, this is what we have previously seen. This is the inequality for autocorrelation coefficient between -1 and -1 and +1. Okay? So how about this one? Expected value of z square, expected value of x square. So this is Rx of 0. This one is square of this. That is Rx of 0, because these processes are wide and stationary. Then I have square root, this one, and so on. Again, I get this result. Okay? So this is a second proof. One last proof, because these are very brief, as you see. So what was Rx of k? This is 1 over 2 pi. 0, let me say minus pi to pi. Minus pi to pi. Sx e to the j omega minus j omega k d omega. So what is this? Inverse DTFT. The inverse DTFT of the power spectral density. This is actually the definition. Okay? Well, we have discussed the power spectral density in the last few hours. So what should I do? Well, let me take the magnitude of this. Okay. So I'm over here right now, magnitude. But this is less than or equal to 1 over 2 pi, a positive quantity, minus pi to pi. The magnitude of the argument when summed up. Okay? Well, what is this? This is essentially triangle inequality, you may say. So I'm summing some quantities in the integrand, then taking the magnitude. But if I take the magnitude of this integrand, it's always positive. So when you sum them up, you get a larger sum. Okay? That is essential triangle inequality. But you can also check this. This is equal to unit magnitude. So this is equal to Sx e to the j omega magnitude, because this is unit magnitude. But since this is always positive, or I should say non-negative, then I don't need magnitude for this. So this is equal to, this part is equal to 1 over 2 pi minus pi to pi Sx e to the j omega d omega. Well, this is nothing but the power area under the power spectral density. This is what we call the power of this random process Rx of 0, by definition one more time. Okay? So this is proof number 3. Okay, so it's good that we have remembered this. Okay? So as you see, several different proofs. Now, here is the question. What happens when Rx of, let's say, t is equal to Rx of 0 for a t, this is an integer, not equal to 0. Okay? Again, I'm considering this equality case. So what happens when I have such an equality? Now you can say that previously we have studied such things. When we have such equalities in Cauchy-Schwarz, let's say, or for this one, then we see that there is a perfect predictability going on. Okay? So, for example, in this case, we know that if I have an equality in this Cauchy-Schwarz, z random variable and w random variable are linearly related. Okay? So that is the case when we have full correlation, isn't it? Fully correlated random variables. So can I see this one for the random processes and autocorrelation sequences? So what is the impact of this statement? But before that, let me give a definition. Okay, I will answer this. Let me write answer. But before giving this answer, I would like to mention mean square periodic. Mean square periodic processes. So this is a definition. A process, a random process, is said to be, this is, let me write mean square, okay. Mean square, or MS, periodic, if expected value of x, let's say n plus t minus x of n, let me put square brackets, parentheses square is equal to 0. Okay? But this is for all n, and of course a non-trivial t which is not equal to 0, otherwise you don't have an interesting statement. So this is, well, for a deterministic case, if there is no expectation, let's say, then x of n, so this, you may say this is the period of this discrete time sequence and so on. But since this is random, now we see that, so samples of this random process separated by t lags have, let's say, 0, you may say power, ensemble power, second power. Or if the process is 0 mean, have the error is 0 variance. Okay, things like that. Okay. Mean square periodic if we have such a case. Okay, note. Expected value of x n plus t minus x of n parentheses square is equal to what? Well, this is expected value of x square n plus t minus 2x of n plus t plus x of n square. Let me put square brackets also. Not so critical, but okay, I have things like that. So how about this? This one is for a White-Sand stationary process. Otherwise, you know, that becomes too general. So we don't have such properties. This is Rx of 0. So this is White-Sand stationary minus 2Rx of, well, this is minus t, if I do it like this, plus Rx of 0, but this is of course equal to Rx of t. Okay. So if random processes mean square periodic, then, you know, this is what we see as the following. This is equal to 0. Rx of t, Rx of 0 is equal to Rx of t for some, you know, for some t not equal to 0, obviously. Okay. So this is the same as this because I have just expanded this square. Okay. Again, I'm talking about in this course, for the rest of this course, about White-Sand stationary processes. Okay, so this is the implication. So if I have something like that, then we see that I have this mean square periodicity in this process. Okay, so what's the meaning of that? Well, let me further think about that. So this is node 2. Let's say this is node number 1. If Rx of 0 is equal to Rx of t, okay, that is, in brackets, let's say, a mean square periodic random process, if I have something like that, then here is the case. Rx of k is periodic with k, with t. That is, Rx of k is equal to Rx of k plus t for all k. Okay? So how can I show this? This is like a claim. Okay? Let me say this is a claim. So if I have mean square periodicity, or if I am at this equality condition, this was our question, then I have this also. So what's the meaning of that? Or how can I show this? So here's again proof. Again, I will use this Cauchy-Schwarz z square expected value of w square, and I have the square root. Now, let me introduce z as, over here, x n plus k plus t minus x n plus k. W is x of n. Okay? Then introduce this one for this one. Introduce w for this one. Okay? Then what do I have? If I have such a case, on the left side, I have the product of these. So I have Rx k plus t, this, or Rx k plus t, okay, minus Rx of k, this times that after expectation, is less than or equal to, now insert over here, the square of this. I have done such a square over here, so the first one squared, cross term, second one squared, okay? So I have 2Rx of 0, square of this expectation, square of this expectation. Their cross term, their lag separation is t, times square of this, one more Rx of 0, and I have this square root over here. Okay. So this is not 0. Otherwise, the process will be, 0 power or 0 variance if it is 0 mean. How about this one? Well, this one, by the claim, this part is equal to 0. So this is equal to 0. So what do I have? I have such a case. Okay. So what I see is the following because of this. Now, if I have if I move, let me see, this to this side, now I have a little bit more interesting result. Okay. So I have taken the square of this is less than or equal to this. Then what I see from this one is Rx of k plus t minus Rx of k. This is less than or equal to 0. Okay. So this is equal to Rx of k plus t is equal to Rx of k. This is clear. So as you see, over here is k is arbitrary. I can select k in any way that I like. So this is valid for all k. Okay. Not only for k is equal to 0, but for all k. So what is the conclusion? The conclusion is this. So if Rx of 0 is equal to Rx of t, equality condition, then Rx of k is periodic with t. So what do I mean by this? Assume that your Rx of 0 is Rx of k. Let's say this is 10. And it happens to be that you observe that Rx of 5 is also 10. Okay? And you know that this is something like this. So next, you know that this is periodic by 5. So this is, let's say 6, this is 3, this is 7, this is maybe 4. Okay? So I have, again, this periodicity. Okay, this is 10, 10, and so on. I have this periodicity like the 6. Okay? Of course, this is, going for both sides. This is what? 7, 10, this is minus 5. Okay, I have something like this. So what I see is that as soon as I see that this autocorrelation lag 0 is matched with equality at a non-zero autocorrelation lag, then I know that whole autocorrelation sequence is periodic. Okay, good to know. So let me have a case then. Okay, these are all deductions from, this condition, equality condition. Then let's assume t is equal to 3. Okay, that is Rx of k is equal to Rx of k plus 3. Okay, so then let's assume, just for the sake of illustration, t is equal to 3. Is it 3 in my example or 4? Let me see. Okay, it's 3. Then let me construct such a matrix, or not a matrix, but let me first write the vector, x vector. So this is again x of n plus 1, n plus 2, n plus 3. Okay? So let me write autocorrelation matrix for this. Rx 0, Rx minus 1. So I have 4 by 4 autocorrelation matrix. So what is this? This is the expected value of x times x transpose, which we call Rx. Okay, autocorrelation matrix. Is this correct, by the way? So this entry is, for example, xn times xn minus 1. After expectation, it becomes Rx minus 1. But it's also equal to Rx1 for real valued case. Okay, very good. Now what do I know? If this is equal to, if the period is equal to 3, I know that this is equal to this. This is equal to that, because if I add 3 to this, I get 1. If I add 3 to this index, I get Rx of 2, and so on. So what do I see? Well, this column and this column, okay, they're equal to each other. So what is this case? So this is the case when this autocorrelation matrix is singular, isn't it? Again, we see some implications related with predictability. Okay, this process is predictability. So what do I mean? So let me write over here. So clearly, if Rxk is equal to Rxk plus 3 for all k, then autocorrelation matrices which are with, let's say, 4 by 4 dimension, with dimensions, or let's say higher dimensions, 5 by 5 or higher, are singular, let's say, are singular. That is, Rx of 0 is greater than or equal to Rx of autocorrelation matrix is, this is our symbolism, greater than or equal to 0, meaning that Rx is positive, semi-definite, semi becomes important, but not positive definite, because it is singular. So what's the meaning of this? Well, the meaning is this: there exists a non-trivial vector which is in the null space of this Rx matrix, isn't it? Okay. There exists a non-trivial vector, so there exists a non-trivial vector, let's say V, and V not equal to 0, non-trivial, in such that, let's make it shorter, such that R times V is equal to 0 vector, because this matrix is a singular matrix, so it has a non-trivial null space. And since, let me write Rx, this is expected value of x transpose, okay, then if I multiply, we have done something like that before, V transpose and V, okay, I can do this. I multiply, well, this is, let me say this, then this is equal to expected value of x transpose V, let's say parentheses square. Okay, I move the V vectors in, as we have done such things before. So how about this? If you check this, then from this side, this is also equal to, but this is also equal to V transpose expected value of, this is equal to Rx times V And since Rx times V is equal to 0 vector, this is also equal to 0. Okay? 0 vector inner product with V. So then I have the equality of these two. So what do I see? The conclusion is there exists a non-trivial V vector so there is a non-trivial linear combination vector V such that V, this is a vector, such that, let's say, xn plus 3 becomes perfectly predictable from the earlier samples, such that one of the samples in x vector becomes perfectly predictable from others. So, in other words, if this is an equality, now this has to be equal to 0. Meaning that if you check this, xn plus 1, xn plus 2, and xn plus 3. This is my x transpose vector. Times v is equal to, let me write 0 over here, is equal to 0. Okay? So you see that there is a linear relation between the samples of X process. Okay? So if you have any, let's say 4 samples like that, let's say n plus 3, move it to the other side, it becomes a linear combination of the 3 samples. Okay? So is it surprising? It's not very surprising because, you know, the process is periodic, you may say by 3. Okay? So it is supposed to be predictable like that. Okay? But as you see, this is extending our general ideas about periodic sequences to the random processes. Okay, very good. So we have seen such interpretations. Now one more interpretation. Finally, let's say, if Rx of k is periodic by t, that is, Rx of k is equal to ak e to the j 2 pi over t, k is from 0 to infinity. Okay, let's say. Okay. So what is this? This is the Fourier series. So this is the Fourier series, as you see. When k is equal to 1, sorry, this is what? So let me do this. L. Okay. L and k. Okay. When L is equal to 1, so what do I see? I see A1 times L is equal to 1, something periodic by t. When L is equal to 2, I see something periodic by t over 2, and so on. Okay? So this is what we call the periodic, Fourier series expansion. Okay? So all of this right-hand side is periodic by t. Well, then what else? If I take its Fourier transform, now I'm writing the same expression in the Fourier domain, 0 to infinity, AL. Well, there's this 2 pi factor, delta, omega, 2 pi over t, L. Okay? So what is the Fourier transform of this? So e to the j, omega naught times k. Okay? So this is omega minus omega naught. Okay, so this is a direct delta over here. So if I sketch this, so in, let's say 0 to 2 pi, I see the following. I see an impulse over here. I see another impulse. So the first one has weight A1, the second one A2. It goes like this. Okay. Let me do not write this upper summation index, because eventually this will repeat. Okay? Let's do not mention this. Let's do not get into details. So this is the nth one, and so on. So this is Sx e to the j omega. So what do I see? So this is the impulsive power spectral density. So whenever you observe an impulsive power spectral density, then you have this, then you have this periodicity, then you have predictability, then you have all of these other things. Okay, all of them are equivalent, as you see. Okay, so everything has started with this. Rx of 0 is equal to Rx of t, and we immediately end up with all of these results. Okay, so actually there is a theorem. This is called Wold's decomposition theorem. And that is the final thing that I would like to say about periodic or harmonic processes. So this is from Hayes's textbook, but let me write this. Wold's decomposition theorem says that an arbitrary process can be, let me see, written as so what is this? This is the arbitrary process, its predictable part and its regular part, where xp of n is the predictable part. So predictable part is, this impulsive spectrum. Predictable part, and xr of n is the regular part. Okay? Where xp of n and xr of n, regular part, are orthogonal to each other. So what's the meaning of that? xp of, let's say, sequence xr of this sequence is equal to 0. Okay? For all mn. Let me put conjugate over one of them. Okay? That is it. So what is the importance of this? This is from page 107 from Hayes' textbook. Okay? It's actually this statement. What's the importance of this? Now you can see that if you have a power spectral density like that, let's say this is up to 2 pi, something like this, and you see some Dirac deltas, let's say 2 of them, something like that. Okay? So this is the predictable part of this process. This is Sx e to the j omega. Predictable part is related with this, impulsive power spectrum, and this is also called line spectra, because in the spectrum analyzer you can see very huge lines on the spectrum analyzer, or you may see this is at a single point in the spectrum, it's like a line in the spectrum. This is called line spectra. So this line spectra corresponds to this predictable process, and the other continuous valued part of this power spectral density corresponds to this regular process. Okay? So this is Wold's decomposition, and immediately you can see that for this process, there is some parts making this autocorrelation matrix, singular, as you see over here. And if you decompose that, this autocorrelation matrix of this regular process, you have that. And this is like the addition of two different autocorrelation matrices. One of them is, perfectly predictable processes autocorrelation matrix. The other one is, this is the process with continuous value. It's not perfectly predictable, but they are uncorrelated processes, so their autocorrelation matrices add up. And for this one, you have a single autocorrelation matrix. For the other one, you don't have that. Okay? Well, that is it. Maybe we should be more careful, but you don't have that. For the line spectra, you surely have this singular autocorrelation matrices. For other one, you have to check. Maybe we should say it like that. Very good. Now, let me give, so we have done this before, so I will just mention it. So if I have a process like this, example, x of n, 1 to L, AL, omega L plus theta L, AL, theta L. So these are independent random variables. Okay? And let's say theta L is uniform in 0 to 2 pi. Okay? Independent, let's say IID, independent and, let me write IID over here, IID random variables. So previously we have derived this. Now you remember that our x of k for this one is autocorrelation. So this is expected value of, this is square e to the j omega L times k, and that is it. Okay? Because you do n minus k, you do this product for the first one, let's say. Then you have exactly that one, thetas cancel. Let me put parentheses over here, and so on. Okay? Then what is power spectral density? You know, this is 2 pi delta omega minus omega L. And indeed, you have exactly something like this. Okay? So you have impulses located at omega 1, impulse, let's say, located at, let's say, something like this, at omega 2, and another impulse at omega L. I have something like this then, Sx e to the j omega, and this one, let me write one of them, has the weight of AL square, so we denote weights with this bracket. Okay? Let me also denote these weights with bracket. That is it. So this is of course periodic by 2 pi and so on. So what we see is that this is the kind of process that I'm talking about when I say, this is just an example of course, this is one of the examples for periodic processes. And no surprises, all of these realizations are also periodic. Okay? Very good. Okay. Now that is the end for this harmonic processes. This is the last type of the processes, and as you see, this corresponds to this important class, and it has some features related with singularities. What do I mean by singularities? This impulsive spectrum, perfect predictability. So these are like the singular cases of the general discussion. Okay, so let me erase this and start our next topic. So all of these topics, types of processes, please also check Hayes's textbook around these pages. They are also explained very well over there. So let me erase also this. Let me start from this part. Now the next we have an important topic, but I will cover this topic somewhat faster, hopefully. So this is called spectral factorization. But before starting this topic, again, let's remind ourselves what we have done. Now I have a filter, H of C. Okay. So this is, let's say, white noise. So what is the meaning that PW? Sometimes we use P, sometimes we use S. Okay, something like that. Even this number can be 1. It's not very critical for our purposes. Okay. Unit variance, white noise. So this is the power spectral density of this. So this is the variance of the process, and so on. So this is setup number 1. What do I mean? So this is called the synthesis. So input white, filter fixed, and output becomes a random process with, let's say, power spectral density with Sx e to the j omega, or let's say Sx of z, because it will be more important. I have something like that. If somebody gives you the filter, so you can synthesize this process with power spectral density Sx of z by this filter. Okay. So as you see in the spectrum, you see 2 factors, and this is connected with this topic, spectral factorization. So this is number 1 is, so this is number 1, this is this number 1, synthesis. Okay. Number 2, now assume that I have this random process. This is the inverse problem. Now you have a G of C, and you want to have a white noise over here. White noise. So this is random process with Sx of C, let's say given. Let's say H of C, H, something given to us. Okay? So now the question is, number 2, this is the 2. This is called the whitening problem. Whitening. So input, let's say x of n with Sx of C. Okay. Output is white. Question is, so how to find, for example, the G of C whitening filter given, let's say, Sx of C. You can immediately see that previously we were discussing decorrelating vectors, isn't it? So this is like decorrelation operation, but I have an infinite dimensional vector over here because, this is not finite dimensional. This is running, it's a random process. This random process is taking values with the samples from minus infinity to plus infinity, but it's the same process. So I would like to decorrelate this random process. This is called, this time, whitening filter. I'll be doing this with a filter. So what's your guess? Like if G of C is 1 over H of C, then there's a cancellation, isn't it? Well, maybe something like that. Okay? Or if I generate this x of n by this H of C, then if I cascade these 2 filters, clearly 1 over H of C as G of C, reciprocal of this over here and cascade it, you're going to gain white noise, provided that, of course, 1 over H of C is a stable filter. If it's not stable, then all of these discussions are not useful for us, because if it's an unstable filter, now I have infinities at the output. Okay? So I'm assuming this. So again, synthesis problem is, now you are synthesizing a random process with a desired power spectral density. Whitening problem is, now given this process with non-white, as you see, spectrum, power spectral density, then find a filter such that output is white. So this is called the whitening. Of course, these problems are, inverses of each other, you may say. Now, we would like to discuss this problem on an example. Let me see. Example. Okay, let's use Px of e to the j omega. I'm using different notations on purpose because, different textbooks use different notations, and these symbols do not mean much other than their meaning. Okay, they are just pointers to a meaning. So I don't want to use the same symbols. I want us to be alert on this actually. Okay, I have power spectral density like that. So first of all, do you think this is a valid power spectral density? Previously we have discussed this. Any power spectral density is valid provided that it's positive valued or non-negative valued. So numerator is always positive, denominator is always positive. So their ratio is positive. It looks like a reasonable power spectral density. Now from our earlier information, I am sure that there is a process corresponding to this. Okay. So how do I generate that process? I don't know yet, but that's question number 1. Okay. So let me see. 1. Find h of c when excited, meaning that input side, when excited with white noise with unit variance, the output process has, let's say, power spectral density as px e to the j omega. Number 2, find g of c, okay, such that when x of n with power spectral density px j omega is at the input of system g of c, the output is white noise. Okay, so this is the second problem. So this time I'm giving this power spectral density. The question is, you are given this power spectral density at the output, find this filter. So similarly, I am given this power spectral density as such, then find the filter such that it's decorrelating. The output becomes a decorrelated version of this. Okay. So how can I do this one? So maybe just to be clear, so this is the synthesis. This is the whitening problem. Okay. So let me work on the solution. Px e to the j omega. So I'm given this. 5 minus 4 cosine omega, 10 minus 6 cosine omega. So how about this? 5 minus 4 times e to the j omega plus e to the minus j omega divided by 2. Divided by, because this is cosine. Okay? So this is 10 minus 6 e to the j omega plus e to the minus j omega divided by 2. Okay? Well, there is some cancellation going on. How about this? I'm writing this as 5 minus 2 z plus z inverse divided by 10 minus 3 z plus z inverse. Okay? So what's going on? What is this z? Now I'm assuming that this z is equal to e to the j omega. So I think it's clear right now. So you may say, I am generalizing this let's say function. It's actually a big step. This function on the unit circle, defined on the unit circle, z is equal to j omega to the complex plane by such a simple operation. Okay. This is actually somewhat a big step, but for our purposes, this becomes px of c, because there is a perfect match on the unit circle, and this is good enough for our purposes. Okay, I have something like that, px of c at the end of this simple calculation. I get that. Now what's my goal? Well, my goal is this. For the first problem, output process, I'm talking about the synthesis problem. If I have white noise over here, then the output is equal to this one for the given h of c. So I want this one to be, this should be equal to h of c. I don't know h of c yet, but h conjugate 1 over z conjugate and so on. Okay? So this is the part where factorization will come into the play. Okay? So excited with white noise, at the output, power spectral density for an arbitrary h is in this form, but I know that x's power spectral density is this. I have this. Do you remember previously we were discussing similar problems, how to synthesize, for example, an AR process, okay, or an ARMA process, and so on. So there was a difficulty with moving average process and ARMA process, because at the end, for the moving average and the ARMA process, we end up with nonlinear equation systems. Okay. Only for the AR process, we end up with Yule-Walker equations, and Yule-Walker equations were linear. We were able to solve these filter coefficients, remember the A vector, very easily by inverting a matrix, essentially, by solving a linear equation system. But for the moving average process and for the ARMA process, it was much more complicated. Okay? So moving average part creates a difficulty. Now you see that this is an ARMA process actually, maybe much more clearer from this because it has both poles and zeros. So I'm trying to find a filter to realize an ARMA process, okay, by spectral factorization. So again, the same problem, essentially. So I need to factorize this. To do the factorization, I want to do the following. I want to multiply, because the Z inverse is creating me some, I'm not used to working with Z inverses. So let me multiply by minus C and minus C, numerator and denominator. So what do I get? I get 2z square, am I right? Minus 5c plus 2. This one is 3z square, this one, 3z square minus 10z and minus 3. Okay? If I multiply by, well, right now I can do this factorization because I will find the roots of this. So you can maybe easily see this, 2z minus 1. Z minus 2. Let me see. 2z square minus 4 minus 5 plus 2. Okay. So this is indeed the result. I can find the roots, etc. But 3z minus 1, z minus 3. This is plus 3 then. Okay. Because this times that gives you plus 3. Let's check one more time. 3z squared, 9 plus 9, minus 9 minus 1 minus 10, and I have plus 3. Okay, so what else? So let me multiply by, again by this part, let me see, 2z inverse minus z inverse. Okay, let me multiply by minus C inverse and minus C inverse, minus C inverse. And I will be ending up with 2z minus 1. So minus C inverse times this, 2z inverse, this cancels, minus 1, divided by 3z minus 1, and this, I have minus 1, this one and this one. I have 3z inverse, okay? So this is my px of c. I haven't done anything other than, simple factorization. Factorization of the numerator polynomial and the denominator polynomial. So you may wonder, there is some, issue. So what's that issue? If this is a valid power spectral density, if problem is correctly, let's say, defined, then this should be equal to, this is our synthesis problem, a filter transfer function times filters transfer function with the reciprocal variable. Okay, I should have such a relation. Now from this, if I can recognize, if I can construct an h of c, I am done. Okay, So how can I construct an h of z? That is the issue. So you may say, well, this is very easy. First of all, this conjugate does not do anything. Well, why it doesn't do anything? If these coefficients are all real, it doesn't do anything, because when you take the conjugate of this expression, you get z conjugates also over here, but these coefficients stay the same. So this becomes conjugate of the conjugate if you do this operation. So you may forget about the conjugates for this calculation. Okay? So how about this? If I select my h of z as this term, 2z minus 1 over 3z minus 1. If h of z is this, what is h of z inverse? It's this part. This is the reason that I have done this, manipulation, just to see it very clearly. Instead of z, if you put z inverse, you get this one. Instead of z, you put z inverse, you get the other one. Okay. So you may say that, okay, this is the end of the problem. This is the end of the problem, but let me see. Okay, so let's continue. So we were at this point. So if I can select like this, then h of 1 over z, it will be that one. Okay. So how about this? Let me select last two. Of course, when you replace z by z inverse, you get the other one. I think you get the idea. So I have four possible choices. 2 z inverse minus 1, so there is one more choice. 3 z minus 1. Okay. So I have four different choices, as you see. Okay. So which one am I going to select? You may say it doesn't matter. It doesn't matter because at the end, if you do this multiplication, you always end up with such a filter. But let's be careful, because from a signal processing viewpoint, let me try to sketch the pole zeros of this. Px of c, pole zero diagram. So I have a 0 at 1 over 2. Let me put the unit circle, because you may remember this is critical for stability. I have a 0 at 1 over 2. Now I have a 0 at, this is when z inverse is 1 over 2, I have 0 over here. I have a 0 at 2. No surprises, they appear in conjugate reciprocal pairs. Okay, this is called conjugate reciprocal, please remember. We always have similar topics coming up. Now I have 1 over 3, this is a pole. And I have a pole at, let me say this is at 3 over here. Because it's 1 over 3, this conjugate reciprocal pair 3. Okay, so this one, well, 0 at zk at, let me say 0. How should I write this? This has 0, 1 over 2, pole 1 over 3, this one. Okay, how about this one? This one has 0, 2, 0, 1 over 2, 0, 2, this is pole, this is 3, this is pole 3, this has pole 1 over 3. So all of them corresponds to different pole 0. Okay, so of course they have the same power spectral density, but they are different filters. So how should I select this? Is there a reasoning? So first of all, I want my filters to be stable. And of course, we want, not assume, but this is what we want actually. We want a causal and stable, let's say h of c. because from a signal processing viewpoint, that makes sense. I don't want to have anti-causal filters or unstable filters and so on. So what's the meaning of that? I want to include this unit circle. Let me have this unit circle in my region of convergence, and I want to have region of convergence extending to infinity. Okay? So which one of those have such a feature? Well, then the pole should be, for stability, included inside of this unit circle. Pole, you see, 1 over 3. So what we see is, let me describe this. This one, let me see. This is stable, causal, am I right? So I can define the region of convergence as outside of this 1 over 3 radius with circle 1 over 3. Okay? I can define it as outside of this. So it will be a right-sided sequence. It will be stable because unit circle is included over here. So how about this one? Pole is at 3. So I want to include this. Then region of convergence should be towards this, 0. Towards, you'd say, it should be inside of this circle. So this one, well, to have this stability, so my comment is stability and causality is not jointly possible. Okay? Because if you want causality, you should go to outside of this unit circle with radius 3, but then it won't be stable. Okay? So similarly for this one. Okay? Because this has a pole at 3, one more time, and you want to include this unit circle, then it has to be anti-causal. Okay? Unfortunately, it has to be like that. How about this one? Okay, this is stable and causal filter is possible. Again, one more time. Okay, stable and causal filter is possible. So of two of these choices make sense. But the other two, in terms of causality and stability, does not make sense. So as you see, very, let's say, elementary knowledge of 301, first signal processing courses coming into play. Okay? So we are deducing these results by our knowledge of basic 301. So what else? Note that h of z, this one, first one, 2z minus 1 divided by 3z minus 1 has all poles, it has a single pole what, and all zeros inside the unit circle. So these two, inside the unit circle. 1 over 3, 1 over 2. 1 over 3, 1 over 2. Such filters are called, in the literature, maybe you can remember, minimum phase filters. It has some additional advantages, but I won't be discussing those additional advantages, but this is a definition. Minimum phase filters and minimum phase, mean phase filters are causal, obviously, we have discussed this, stable, and causally invertible. So what does this mean? Okay, what does this mean? So H inverse, let's say, inverse of C, if I define as 1 over H of C, inverse of this operation, inverse mapping, inverse transfer function, you may say, then you see that poles and zeros, they interchange their places. In this example, it becomes, so inverse filter obviously has a pole at 1/2, 0 at 1/3, because reciprocal. So this is previously a pole. At the inverse filter, this becomes a 0, and vice versa. Okay. So all of those conclusions are again correct. Causal, stable for the inverse filter. Well, it's exactly the same. And what we see is it's causally invertible then. Okay. So this is a very important conclusion. So if I am processing so if we are processing a random process x of n, let's say there is a processing chain, I can always process this by this let's say inverse filter, or I can put this, or I can put its inverse. I can always go back and forth. Okay, so let's say this is y, so this is z. Okay, so in other words, in this processing chain, I can apply this filter h of c to this x of n process. But if I decide that, well, I shouldn't have applied it at the very beginning, no harm is done. There is no loss of information. You can always apply this inverse filter, and you can always come back this original. Let me write this x of n. Okay, original random process. You retrieve it back. But this is a causal operation. This is a causal operation. So it seems that this is like a lossless operation. You are not losing any information, and that is it. Okay. Very good. So we have found this as a good choice for a synthesis filter, because if I synthesize by this, then I can construct this inverse filter. Then it will be also a causal and stable filter. Its inverse will be again causal and stable. So h of c, let's say 2z minus 1 divided by 3z minus 1 is a possible choice for synthesis filter. So this is the minimum phase choice, minimum phase filter. This one is also possible. 2z minus 1 divided by 3z minus 1 is also a valid choice, but its inverse is not stable. Maybe you care about its inverse, okay? Just be careful, okay? Because its inverse, because it has, this one has a 0 at 2, its inverse has a pole at 2, it's stable and causal, let's say. Stable and causal, okay? That is it. Now the second question, this whitening question, this part, I think we have answered it already. Number 2, whitening filter. Okay, so x of n is given. I need a g of c, and this is supposed to be white. Okay, well, now x of n is px of c is, what was this, one of these 2z minus 1, 3z minus 1 times 2z minus 1. Okay, so if we select, so this is the power, again the spectral factorization of this given process. We have done it in the first part. Now how can I select such that the output has power spectrum as, let's say, 1. Okay, so it's like white noise for all frequencies, it's constant. Okay, So how can I have this? Now if I select my g of c as, I want to cancel this. 3z minus 1. I want to cancel this one. 2z minus 1. That is it. Okay. So this is the inverse of this, as you can imagine. Okay. That is it. Because remember, earlier we have constructed this in the first part, x of n, by this white noise, by processing by h of c. Then if g of c is inverse filter, then of course you get this original white sequence back. Okay. Of course you don't have to know this. Okay. You can start the problem from here, but this is what we have done in the synthesis part. Okay, that is it. Of course there are some other choices, etc. Same discussions, but this is one of the choices for whitening. But I think in the question it was again asking for always choose this minimum phase filters, because that is the safest way to go. Okay, so this is a minimum phase filter. Minimum phase whitening filter this time. This is minimum phase, synthesis filter. Very good. Let me see. Is there anything else left out? Okay, so that is the end of this lecture. So what else we are going to do? Starting from next lecture. So what we have done, we have studied this synthesis of random processes. Synthesis, like we are finding the synthesis filter and so on. So this is called signal modeling. So previously, up to now, let's say, up to now, we have worked on finding synthesis filters to realize a given, let's say, power spectral density, Sx e to the j omega, or autocorrelation. Okay, something like that. Next, we will try to find filters such that the impulse response, the filter impulse response, let's say realizes realizes a given sequence. So this is called deterministic modeling. This is actually an easier problem. So I'll briefly discuss this. Okay. Then we will continue with other discussions. Okay. So let me just say a few things. This is called stochastic modeling. Okay, there is a stochastic process. So maybe this is like a measurement. I have collected some measurements. So at the end of those measurements, I have a power spectral density estimate, let's say. Now I want to model this power spectral density estimate as the output of a filter. Okay, filter is excited by white noise, but how to find that synthesis filter? Okay, so this is something similar, but this time I'm given a, let's say, impulse response measurement. So I want to find a filter such that this filter's impulse response matches this measurement. Okay, so that will be our next task. So we will continue next time with more discussions. Okay.